Hi viewers, welcome to Quantum Chemistry. In this module, we are discussing Schrodinger wave equation. The contents are introduction, the time-independent Schrodinger wave equation, setting up of Schrodinger wave equation, the wave function psi and significance of wave function. Introduction. Erwin Schrodinger formulated a new version of quantum mechanics that was based on waves and is known as wave mechanics. Erwin Schrodinger wrote down a wave equation which is the so-called Schrodinger wave equation. It should be noted that the Schrodinger wave equation is the heart of quantum mechanics. This is Erwin Rudolf Joseph Alexander Schrodinger. He won Nobel Prize for Physics in the year 1933 for the discovery of new productive forms of atomic theory and also for the formulation of the Schrodinger wave equation. Now, the Schrodinger wave equation. The Schrodinger equation or the Schrodinger wave equation is the fundamental equation of quantum mechanics. The solution to the Schrodinger equation are called wave functions. The Schrodinger wave equation has two versions or two forms. They are the time-dependent Schrodinger wave equation and the time-independent Schrodinger wave equation. The version of the Schrodinger wave equation that does not contain time as a variable is known as time-independent Schrodinger wave equation. Simply means this form contains no time variable. This is the representation of the time-independent Schrodinger wave equation. That is, Hamiltonian psi is equal to energy into psi. The version of Schrodinger wave equation with time as a variable is known as time-dependent Schrodinger wave equation. The time-dependent Schrodinger wave equation in its simple form can be represented as I s cross dou psi by dou t equal to Hamiltonian psi, where h hat, as you know, is known as the Hamiltonian operator or the total energy operator. Now, time-independent Schrodinger wave equation. The Schrodinger equation is a partial differential equation. That is, it describes the dynamics of quantum mechanical systems through wave function or psi. Solutions to the time-independent Schrodinger equation are called stationary state wave functions because they are independent of time. This simply means that here the solution of time-independent equation are called stationary state wave functions. Stationary state means the wave function that is independent of time. Hence the solution are called stationary state wave functions. Moving on to the complete form of time-independent Schrodinger wave equation. This is the complete form, that is dou square psi by dou x square plus dou square psi by dou y square plus dou square psi by dou z square plus 8 pi square m by h square into e minus v into psi is equal to 0. In this equation, psi represents the wave function, m represents the mass of the particle under consideration, h represents Max Planck's constant, its value is equal to 6.626 into 10 raised to minus 34 joule second. E represents the total energy of the system and V represents potential energy of the system. Hence, E minus V stands for total energy minus potential energy, that E minus V equal to kinetic energy associated with the system. This equation can be again simplified to del square psi plus 8 pi square m by h square into E minus V into psi is equal to 0. Here, del square represents the so-called Laplacian operator or Laplace's operator. This equation can again be simplified as Hamiltonian psi is equal to E psi. This is the most simplified form of the time-independent Schrodinger wave equation. Now, we can move on to the setting up of Schrodinger wave equation. That is, we are going to discuss about the derivation of the Schrodinger wave equation. The Schrodinger wave equation can be derived from the classical wave equation. The Schrodinger wave equation is developed by making the use of wave-particle duality and classical wave equation. The derivation of time-independent Schrodinger wave equation can begin by considering a simple wave motion or the motion of a stretched string like that. Now, consider a wave traveling in a string along the x direction with velocity equal to v. The picture represents such a wave motion, and here it is clear that the wave is propagating along x direction, and the height of the wave that is taken as y, or y represents the amplitude. Y is the amplitude of this vibration at any point whose coordinate is x, which is at any time t. This is the description of a classical wave. Now, the expression describing such a kind of wave motion is like this, that is dou square y divided by dou x square equal to 1 by v square into dou square y divided by dou t square. Here, v is the velocity with which the wave is propagating. It is clear from this equation 1 that the amplitude phi depends on two variables, namely the coordinate x and time t. Here, x is the direction through which the wave is propagating, and t is another variable. That is, amplitude depends on x and t. In order to solve the differential equation that I shown earlier, it is necessary to separate the two variables present in that equation. That is, the two variables are x and t. As a first part, we have to separate the variables x and t to solve the equation describing the wave motion. Thus, since y consists of two variables, we can represent y as a function of two variables, that is f of x and g of t. Simply means y is equal to f of x into g of t. Here, f of x is a function of the coordinate x only, and g of t represents t, or the function that depends on t only. Now, for stationary waves like wave motion of a stretched string, the function g of t can be represented as g of t is equal to a sine 2 pi nu t, where a represents a constant, nu represents the vibrational frequency, and keeping a as a constant, which is known as the maximum amplitude. On substituting the value of g of t in the previous equation, that is y is equal to f of x into g of t, we will get y equal to f of x into a sine 2 pi nu t. Now we can derive Schrodinger wave equation like this. We have the equation of a wave as dou square y by dou x square equal to 1 by v square multiplied by dou square y by dou t square. Dou square y divided by dou t square. And we know that y is equal to f of x into g of t. But g of t is equal to a sine 2 pi nu t. That is, y is equal to f of x into a sine 2 pi nu t, where nu represents the frequency. Hence, I can do like this, dou y by dou t, that is differentiating this quantity with respect to t first, that is dou y by dou t. Here f of x is a constant, a is also a constant, therefore, the term is, the result is a cos 2 pi nu t multiplied by 2 pi nu. I am differentiating it once again to substitute here. Therefore, dou square y by dou t square is equal to f of x into a cos 2 pi nu t is replaced by minus a sin 2 pi nu t. So, I have to put a minus sign, minus a sin 2 pi nu t multiplied by 2 pi nu, again one more 2 pi nu, and the result is minus f of x into a sin 2 pi nu t into 4 pi square nu square. And this term is simply g of t. That is, g of t is equal to a sin 2 pi nu t. Here also a sin 2 pi nu t term appears. Hence, dou square y by dou t square is equal to minus f of x into g of t into the last term, that is 4 pi square nu square. This about dou square y divided by dou t square. And I have to substitute the result of dou square y by dou t square in this equation. Hence, I will get dou square y divided by dou x square equal to 1 by v square into this term, that is minus f of x into g of t into the last term, that is 4 pi square nu square. 4 pi square nu square. Now, this is the term on the right hand side. Now, moving on the left hand side. Left hand side y is equal to, we already know f of x into g of t. Therefore, dou y by dou x equal to g of t into dou f of x divided by dou x. Similarly, the second differential, dou square y by dou x square equal to, again g of t keeping as a constant since we are performing partial differentiation, the term will be dou square f of x divided by dou x square. And we have to substitute dou square y by dou x square by g of t into dou square f of x by dou x square. Hence, I will get the equation g of t into dou square f of x by dou x square equal to minus 1 by v square f of x into g of t into 4 pi square nu square. 4 pi square nu square. Here we can cancel g of t terms from LHS and RHS. And this vanishes the time part, the time variable. Hence, on proceeding in continuation, we will get an equation that is totally independent of time. Hence, the name time independent Schrodinger wave equation. That is, we are getting dou square f of x by dou x square equal to minus 4 pi square nu square by v square into f of x. Minus 4 pi square nu square divided by v square into f of x. Now we got the relation dou square f of x by dou x square equal to minus 4 pi square nu square by v square into f of x. It should be noted that the frequency and wavelength are connected as nu is equal to c by lambda. Nu is equal to c by lambda, where c represents the velocity of light. Now we are discussing with a wave propagating with a velocity v. For convenience, this c can be replaced by v. That is, we get nu as v by lambda. I can replace nu square by v square by lambda square. Hence, I got the relation minus 4 pi square v square divided by v square into lambda square into f of x. V square vanishes. And the RHS will be equal to minus 4 pi square by lambda square into f of x. This is equal to dou square f of x divided by dou x square. And we know about the de Broglie relation. That is, de Broglie relation is the wave particle duality relation. The wavelength lambda is connected to momentum of a body by the relation lambda is equal to h by mv. Therefore, lambda square equal to h square by m square v square. We can substitute this lambda square here to get the relation minus 4 pi square m square v square, that appears in the denominator, now came in the numerator, divided by h square into f of x. Now I can do one more correction. We know about kinetic energy of a system. That is, the kinetic energy of a particle of mass m moving with a velocity v is given as kinetic energy is equal to half mv square. And we know the fact that kinetic energy and potential energy will give the total energy of the system. That is, half mv square is the kinetic energy term, and let capital V represents the potential energy. Then kinetic energy plus potential energy, that is equal to total energy. That is, half mv square equal to total energy minus potential energy, or mv square equal to 2 into E minus V. Or here there is a term that is m square v square. Here we have mv square, or m square v square can be equal to 2m into E minus V. Therefore, m square v square in this equation can be replaced with 2m into E minus V. Thus, I get dou square f of x divided by dou x square is equal to minus 4 pi square into 2m into E minus V into f of x divided by h square. Thus, I got the relation dou square f of x divided by dou x square equal to minus 8 pi square m by h square into E minus V into f of x. This equation represents the motion of a wave along x direction only. We can extend this to 3 dimensions. In order to extend this equation into 3 dimensions, I have to make a replacement. That is, the term f of x present in this equation should be replaced by psi of xy z, where psi of xy z is the wave function. On replacing f of x by psi of xy z, the form, this differential form also changes, and we have to represent the left hand side like this: dou square psi by dou x square plus dou square psi by dou y square plus dou square psi by dou z square. That is the left hand side. This is, here we are having 3 variables x, y and z, and we are differentiating with respect to x, y and z in each case twice partially. And this is equal to minus 8 pi square m by h square into e minus v into f of x is replaced as psi of xy z, psi of xy z. And the right hand side can be shifted towards left hand side to get RHS as 0. That is, we are getting the final relation dou square psi by dou x square plus dou square psi by dou y square plus dou square psi by dou z square plus 8 pi square m by h square into e minus v into psi of x, y, z is equal to 0. This is known as the time independent Schrodinger wave equation. In this equation, there is no time variable, and the 3 variables are x, y and z. Only coordinates are the variable. Here there is no time variable, and this is the time independent Schrodinger wave equation. Now we can make further simplifications of this equation. That is, we have the left hand side equal to dou square psi by dou x square plus dou square psi by dou y square plus dou square psi by dou z square plus 8 pi square m by h square into e minus v is into e minus v into psi of x, y, z is equal to 0, into psi of x, y, z is equal to 0. This is the complete Schrodinger wave equation, and this term can be further simplified by incorporating an operator called del square or Laplacian operator. We are getting this left hand side as del square psi. This is because del square or Laplacian operator is dou square by dou x square plus dou square by dou y square plus dou square by dou z square. By invoking del square on this, we are getting this relation del square psi plus 8 pi square m by h square into e minus v into psi of xy z is equal to 0. This term can again be simplified to get Hamiltonian psi is equal to E psi by proceeding as follows. That is, I can split again into 2 parts. That is, del square psi equal to minus 8 pi square m by h square into e minus v into psi or psi of x, y, z. This is the term. And I can change these parameters to left side, that is minus s square by 8 pi square m del square psi equal to e minus v into psi, or minus s cross square by 2m. This term is equal to minus s cross square by 2m, where h cross is equal to h by 2 pi. that is a constant known as Dirac. So, minus s cross square by 2m, that is equal to minus h square by 8 to pi square m. Here this is replaced by minus s cross square by 2m. Minus s cross square by 2m del square psi is equal to E psi plus V, E psi minus V psi. E psi minus V psi. That minus V psi can be come to the left side. That is minus s cross square by 2m del square psi plus V psi equal to E psi. Or here we can take psi as the common factor. That is, we are getting minus s cross square by 2m del square plus V into psi is equal to energy into psi. We already learned that the term inside the bracket represents an operator which corresponds to total energy, that is kinetic energy and potential energy. This bracket is nothing but H hat or the Hamiltonian operator, that is Hamiltonian of psi, that is H hat psi. H hat psi is equal to energy into psi. H hat psi of xyz is equal to energy into psi of xyz. This is the time independent Schrodinger wave equation in its simplified form. Thus, we have derived the time independent Schrodinger wave equation by beginning from a wave motion that describes the motion of a string which propagate along x-axis with amplitude equal to y. We have Hamiltonian psi is equal to E psi, that is time independent Schrodinger wave equation. Now, we can move on to the wave function. The wave function psi is an acceptable solution of the Schrodinger wave equation. We already learned that the Schrodinger wave equation is a second order partial differential equation. It may have more than one solution. In such a case, the acceptable solution, one of the acceptable solution is taken as psi. Psi is an acceptable solution of Schrodinger wave equation. The wave function contains all possible information about a quantum mechanical system. These important properties we learned with the postulates of the quantum mechanics. In one of the postulates, that is called the state function postulate, we already learned that the wave function psi, which is a mathematical function, have certain qualities. In order for a mathematical function to be well behaved, it must satisfy some qualities. The wave function is simply a mathematical function, but that mathematical function must be well behaved. Well behaved means a function should be single valued, continuous, finite and normalized. Similarly, we can say that the wave function psi has all these four properties. That is, the state function psi must be single valued. The wave function psi is continuous, that is whenever you are graphically plotted, there should be no discontinuity is observed. And the wave function is normalized. We already learned the condition for normalization as integral psi star RT psi of RT d tau is equal to unity. If it is not normalized, it should be normalizable. And the last peculiarity, that is the wave function is finite. Thus, the wave function psi is associated with these four important properties. Now, significance of the wave function psi. We know that the wave function psi is an acceptable solution of the Schrodinger wave equation. If we are dealing with the time independent Schrodinger wave equation, psi is known as stationary state wave function. The wave function psi in Schrodinger wave equation has no physical significance except that it represents the amplitude of the electron wave. If electron is propagating like a wave, the wave must have an amplitude. The amplitude of that electron wave is the wave function psi. This is the one and only significance, that is the square of the wave function, that is psi square, gives the probability, that is the possibility of finding electron of a given energy in a given region around the nucleus. This simply means that psi square gives the probability of finding an electron around the nucleus. Now, it is possible to identify the region of space around the nucleus where there is high probability of finding an electron by noting the value of psi square. If the value of psi square is maximum, then the probability of finding that electron will be maximum. The region where the probability of finding of an electron is maximum in space is known as atomic orbital. That is, atomic orbital are the region of space where the probability of finding an electron is maximum. Max Born was a scientist who gave a statistical interpretation of the wave function by naming it as the probability amplitude function. Max Born interpreted psi as probability amplitude function. Now we can move on to Born interpretation of wave function. If psi x is the wave function of a particle which is propagating or which is present along the x direction, then the probability of finding the particle within the range from x to x plus dx, where dx is a small element along the x direction. The probability of finding the particle along the x direction between x and s plus dx is given as px dx equal to psi star psi dx. If psi is real, we can represent psi star is equal to psi, or px dx is modulus of psi square dx. Here px dx represents the probability. That is, probability is related to square of the wave function. Probability equal to modulus psi square dx. The probability is proportional to the square of the wave function. This is the Born interpretation of the wave function. Thus, in this module, we learned about two versions of the Schrodinger wave equation. They are time dependent and time independent Schrodinger wave equation. We derived the time independent Schrodinger wave equation, its different forms we learned, and also mentioned about the significance of the wave function and the Born interpretation. That's all about this module. Have a nice learning experience. Thank you.